Hello everyone, this is Chapter 3, Probability, and beginning in Section 3.1 we look at the basic concepts of probability and counting. First we define a probability experiment, and you could read the formality there, but an example might be rolling a single die. Then an outcome is the result of a single trial. So a result might be rolling a 3, for example. The sample space consists of the set of all the possible outcomes. So for our experiment of rolling a die, as a set, so using braces, the possible outcomes are either a 1, 2, 3, a 4, a 5, or a 6. So that would be the sample space for that experiment. An event consists of one or more of the outcomes, and it is a subset of the sample space. So some examples, maybe you're looking to roll a 3, for example. So the event might be rolling a 3. Or maybe the event is rolling a number that's odd. So it would consist of the 3 outcomes, 1, 3, and 5. We often use a tree diagram to represent the possible outcomes of a sequence of trials in an experiment. And we use branches, as we'll see through our example here. And then just to define the simple event, the situation of rolling the die, rolling a 3 would be a simple event, because it's a single outcome, so that's simple. Whereas rolling the odd number, 1, 3, or 5, is not simple, because there's more than one outcome. But here we want to use a tree diagram to list the sample space for the possible gender sequence in a family of 3 children. Okay, so we're going to use, let's say a dot as the trunk of the tree, for example. And the first time that we perform this experiment, a couple has a child. It could either be a boy or a girl. But then the second trial, having the second child, we would have to work off of each of these branches, because we don't know if it was a boy, and it wouldn't matter if it was a boy or a girl. The second trial is independent of the first, so we could have a boy or a girl off of each of those. And then similarly, the third child that they have can be a boy or a girl out of each of those outcomes. And then you just simply read the branches. The first branch, boy, boy, boy. Second sequence, boy, boy, girl. Third sequence, boy, girl, boy. Then boy, girl, girl. And then those starting with the girl, girl, boy, boy. Girl, boy, girl. Girl, girl, and boy. And finally, girl, girl, and girl. So that's how we use a tree diagram. Now, in terms of counting, we have this fundamental counting principle. If we perform two events in sequence, and the first can occur in P ways and the second in Q ways, then performing them in sequence, they can be performed in the following number of ways, where you take the product of P times Q. And you could extend that to more than two events. So, to consider the example above, we basically have three events: first child, second child, third child. I like to use little boxes here, and the numbers that we put in these boxes represent how many ways that particular event can occur. So the first time you can have one of two choices, boy, girl. Second time, two choices, boy, girl. Third time, two choices, boy, girl. Multiply those together, and we get 8 ways. And you could verify by counting up the number of outcomes. Okay, so here's the second example. Toss a coin, roll the die. Let's say the first box represents the coin. Second box represents the die. There's 2 outcomes for the coin. Okay, and these are going to be multiplied by 6 outcomes for the die. And so we get 12 ways, or 12 outcomes. Okay, now here's a classic example. We've got an access code consists of 4 digits. And each digit can be the numbers 0 through 9. But then we've got some restrictions. Well, actually, the first example, no restrictions. You just have the 4 digits. And they can be repeated. So make sure you know 0 through 9, there's 10 digits. And if they can be repeated, you could put any 10 in the first, any 10 in the second position, any 10 in the third, and any 10 in the fourth, giving you a product of 10,000 outcomes. Now, if the digits are not repeated, we can start with 4 boxes. There's 4 positions to fill. In the first position, we could put any 10 of the digits, but you have to assume that you've used one of them. And that digit that was used cannot be repeated. And you don't need to know what digit it was that was used. The fact is, one of them were used out of the 10, leaving 9 to choose from in the next position. Now, consequently, 2 digits were used out of the 10, so in the third position, only 8 left to choose from, and similarly, in the fourth position, 7. And that multiplied gives you 5,040. And then here's one that's a little bit more interesting. Again, you start with the 4 positions to fill, and the last digit must be odd. If the last digit must be odd, so this is what makes it an odd number, you have a choice of the 1, 3, 5, 7, or 9. So there are 5 digits to choose from that will force the number in the last position to be odd. It also says the first digit cannot be a 0. So if the first digit cannot be a 0, there's 9 digits to choose from in the first position. And then it goes on to say digits can be repeated, so there's really no restrictions on the 2 middle positions. You can put any one of the 10 digits in either of those positions. And multiplying, we get 4,500. Okay, continuing with basic probability. There's 3 main types what we call classical, empirical, and subjective. Classical, when everything's equally as likely. There's a formula, probability of the event, that's how we read this. Probability of event E, P of the E, if you like. It's just the number of outcomes in the event divided by the total number of outcomes in the sample space. A lot of times I like to just think of it as the number of successes, the number of successful outcomes over the total number of outcomes. So you don't really need a formula, it's kind of intuitive. And an example, if we draw a card from a deck, find the probability of getting a jack. So the probability of a jack, I could write it like this if I like. You don't need the notation if you don't want to. Okay, again, I'm going to think of it as success over total. There's a total of 52 cards in the deck, and 4 of them are jacks. So 4 would be considered successful. And then we could reduce that as a fraction to 1/13. Just be careful, in my math lab they might ask you to calculate and round to a specific decimal, whatever the case, but there's a fraction in lowest terms. Probability of the 6 of clubs. Again, I'm going to think success over total, so it's a fraction. Again, there's a total of 52 cards, but the 6 of clubs, that's only one card. So 1 out of 52 for that one, and the probability of a red card. Now, you could just think intuitively 1/2, because you know half are red and half are black, or you could say 52 total and 26 are red, which reduces to 1/2. Okay, and then we look at empirical or statistical probability. This is based on observations. So if we have a table of results that were observed, it's what we call the relative frequency of the event. And it's really success over total. The textbook gives it as frequency of the event over the total frequency. But success over total is what I like to think of. And here we're told we're given a sample of 1,000 people. We want to find the probability. We select 1. Find the probability that their age is between 25 and 34. So we've got the total, which is, notice how this is the frequencies, and this is the sum of the frequency. So that's actually the value of n. But that's our total, so we got 1,000 in the denominator. And out of those, we're looking for the ones that are 25 to 34 years old. So just reading the chart, 25 to 34, looks like it's the 366. And that might ask for the answer as a decimal. So dividing it out, 0.366. Okay, and then the last concept in 3.1, besides the basic probability, success over total, is subjective probability. And that's results from intuition, educated guesses, and estimates. You know, an example of that might be a prediction on how, you know, if it's going to snow today. Like there's a 30% chance of snow. That would be subjective. That would be an educated guess. Your meteorologist would take into consideration the things that might determine that. And then here's some probability rules. If something is certain to occur, probability is 1 or 100%. If something will not occur, probability is 0 or 0%. The probability of anything is always going to be between 0 and 1, so you could actually write this statement: 0 is less than or equal to the probability of x, which is less than or equal to 1. That's always going to be true. Any probabilities between 0 and 1, never negative, never greater than 1. And the sum of all the probabilities is going to equal 1. So you could state that the sum of the p of x's will equal 1. And we say that the set of outcomes that are in the sample space but not in the event, this is complementary events. So for example, if the probability it's going to snow is 30%, you don't need a fancy formula, just intuitively, the probability it does not snow would be 70%. And this is E with a little prime next to it. That's what's meant as E complement. Or you could also say the probability of not E is 1 minus the probability of E. Okay, so in the example 5 from the previous page, it says find the probability of randomly choosing an employee who's not between 55 and 64. What you could do is actually add up all the ones that are not, or you could calculate the probability that they are between 55 and 64, which is again success over total, 1,000 total. There's 125, look at the table, that are between 55 and 64, which is 0.125. So therefore the probability of not being between 55 and 64 is going to be 1 minus the probability that they are between 55 and 64. So therefore 1 minus 0.125 or 0.875, which you could have equivalently obtained by adding up all of those that are not between 55 and 64 and dividing by 1,000. Okay, so that's the end of 3.1. In section 3.2, we look at conditional probability and the multiplication rule. First off, conditional probability, there's a notation here. It's basically means that you're calculating the probability of an event based on another event having already occurred. So we denote it as the probability of B, and the vertical bar is read as given. So the probability of B given A. So we want to know the probability of event B given that event A has occurred. And the key word there is the given, again, is the vertical bar. And this table is referred to as a contingency table. We have a survey, oftentimes we'll have it tabularized, similar to what we have here. If these totals are not given, you're going to want to sum the rows and sum the columns. And then always check that the sum of the rows is equal to the sum of the columns. That's your grand total in the lower right. Now, before we get to the concept of conditional probability and the idea of an event already occurring, the given, we look at some basic ones. Probability of being male. Again, success over total. There's a total of 100. And how many people are male? Well, you look in that row, and there's 50 total that are male. And I'm just going to change these to decimals, so 0.5. Probability of the respondent answered no. Probability of no. Again, there's 100 total. And out of those 100, look at the no people, and there are 60 of them. So 0.6. Was female and answered yes. When we're talking about a contingency table, and we want female and yes in this case. Okay, there's 100 people total, but we're talking about the people that are both, at the same time they're female, they answered yes. So this is actually the intersection of the female row and the yes column. So if you look at the female row and the yes column, the people that are female and yes are these 8 people. Okay, now here are the conditionals, givens. If you want to write it out using notation, it's the probability they answered yes, given that they're female. And when you're dealing with the givens, what I'm going to suggest is this. Say, ask a conditional probability where we're given one event is assumed to have occurred. I'm going to say, think of restricting the sample space. That is, only consider those people or respondents or whatever the case is that have met the given criteria. So in the fraction, the total is going to be the number of females. So I'm restricting the sample space to only the female people. I'm ignoring the males because I'm given that it's a female. So if I ignore the males, you can even cover them up. You're looking at the females. There's 50 of them in total. And so that's going to be the denominator of that fraction. And out of those 50, how many females answered yes? And again, we're restricting the sample space. So you're only looking at the females. And out of the 50 females, the yes column's the first column. There were 8 of them. And that computes to be 0.16. So here's another given. The nice thing about using this notation, if you write it probability of male given they answered no, you can almost think of it as a fraction where the first term is the numerator and the second term is the denominator. You want to focus on the denominator first because you're restricting the sample space to the no people. So now I'm ignoring the yes people. I'm looking at them, covering up the yes people. I'm looking at the no people. There's 60 of them in total. And out of those 60 that answered no, how many were male? And you could see that 18 of them were male. So that calculates to be 0.30. Okay, in the next page we define independent events. And we say two events are independent if the probability that event A occurs does not affect the probability of event B occurring. I use that term when we're talking about the sequence of children. If you have a boy, next time you have a child, probability is still 50%, theoretically. Or maybe flipping a coin. Doesn't matter if you flip a coin 10 times and you get heads each of the times. The next time you flip it, the probability if it's a head or a tail is still 1/2. And then two events are dependent if the probability of the first does have an effect on the second one occurring. And there's two rules for multiplication. If we perform these two events in sequence, this is very similar to the fundamental counting principle. Performing them in sequence, we use two different notations. For independent, just the probability of A times the probability of B. For dependent, we're going to use the conditional probability. First, the probability that A occurred, but then multiplied by the probability of B occurring, given that A has occurred. So we're assuming that A has occurred. And you could extend this to more than excuse me, more than two events. Okay, so you draw a card from a deck. Now, I'm going to try to make this easy. Rather than using, I'll show the notation, but you really don't need it. But here, if I wanted the probability of draw a card, replace it, draw a second card. I want the probability of the first card being a queen and the second card being an ace. So I want the probability of a queen and an ace. So let me just write it that way. Since there is replacement, these events would be independent because the probability of drawing the second card is not influenced by what happens the first time because we put that first card back. So this would just be the probability of the queen times the probability of the ace. Now, a lot of times I suggest don't even bother with the notation. It's your choice. All you're really doing is two fractions multiplied together. First one's a queen. There's 52 total. 4 of them are queens. And the second one needs to be an ace. You would put back the card, so there's still 52, and 4 of them are aces. And multiplying that out and reducing, you get 1/169. Oh, just to show you on the calculator, hopefully you purchased a TI-30 or something similar. This A with the B over C key, fraction key, saves a lot of time. Let me turn it on, clear it. If I want 4/52 times 4/52, I hit 4 fraction key 52. Notice how the little backwards L, upside down L, is the fraction, the way the calculator indicates a fraction. And then I'm multiplying by 4 fraction key 52, and the calculator does all the work for me. There's 1/169. So it reduces and multiplies. So take advantage of that. And again, on my math lab, they might ask for decimals, so whatever the case, just be careful. Okay, Here, person owns 5 CDs. Now this is where I'm going to suggest just multiply the two fractions together. Don't worry about the notation. In this case, there's no replacement because we draw 2 CDs selected at random. If there's no replacement, then the two events are dependent. And the first time we draw a CD, we want to know if both are country music. There's 30 of them, and 5 of them are country music. But then we're drawing a second one without replacing that. And this is where we have the multiplication rule for dependent events. If we took that one CD out that was country music, there are now 29 CDs to choose from, and only 4 are country music. And if you multiply that out as a fraction, it comes out to 2 out of 87, and approximately as a decimal 0.023. Okay, here a study found 62% of households own a computer. Of those, 88% have internet access. Find the probability that they own a computer and have internet access. So you have to determine, are they independent or dependent? And they would be dependent because owning a computer relies on having internet access. So it's basically just the multiplication of, in this case, the percentages. 0.62, change them to decimals when you do the calculations, times 0.88. So 5456. Okay, toss a coin, roll a die, get a tail on the coin, a 6 on the die. Again, just 2 fractions. I want a tail on the coin, 1/2, and you might note that these are independent because whatever happens on the coin doesn't influence what happens on the die. And then, so there's my tail on the coin and a 6 on the die. There's 6 outcomes, and only one of them is a 6. So I'll leave that as 1/12. Alright, and then the final page for section 3.2. First concept, at least 1, is 1 minus the probability of none. It's the complement. At least 1, if you had 0, at least 1 is the complement of having none, or having 0. So sometimes they lead you through the problem like this one. You got 12 light bulbs that are tested, and 3 of them fail. Here we're going to select 2 light bulbs without replacement. So note that without replacement is dependent because the probabilities change. And again, they're just fractions, 2 fractions being multiplied together. The first time, okay, both light bulbs are going to fail. So the first one fails. There's a total of 12. That means we chose the one that failed, and there were 3 in there that failed. So 3 out of 12. But if we're not replacing, the next time we choose one, there's only 11 left to choose from. And if we had taken out one that failed, there's only 2 left that fail. And that multiplied out and reduced is 1 over 22. Then it says find the probability both light bulbs pass the test. Again, just 2 fractions. There's 12 total the first time we draw one. If it passes, if 3 failed, then 9 pass. And then the second draw, there's now only 11 to choose from. And we're assuming that we took one out that passed. So now there are only 8 in there that are left to pass. And that reduces to 6 over 11. And then we have probability of at least 1. So the probability of at least 1, that's 1 minus the probability of none. And the probability of none, so probability at least 1 failed is the probability that none fail, and the probability that none of them fail is the probability that both of them passed. So 1 minus 6 over 11, or 5/11ths. Okay, and then finally a classic example at the end here. Got all these different cans of soda. If you add them all up, 4 root beer, 5 orange, 6 cola, 15 total. We're selecting 3 cans. So now we're going to have 3 fractions being multiplied together without replacement. Means they're dependent. The probabilities are going to change. And so the first one, all are root beer. So 3 fractions. First time we draw, 15 total. We want a root beer. There's 4 of them that are root beer. Next time we draw, we think you drank it, whatever the case, gave it to your friend. There's only 14 left to choose from. And now we're assuming that the first one was a root beer, so there's only 3 root beers left to choose from. And then similarly in the third time we draw, there's only 13 cans, and out of those, only 2 are root beer. And that multiplies and reduces to 4 over 455. Okay, again, it can be 3 fractions. So without bogging ourselves down with the notation, we want the first 2 are cola, third is orange. First one cola, there's 15 total. 6 are cola, so 6 out of 15. Next time that cola is gone, there's only 14 left to choose from, 5 of which are now cola. And now there's 13 cans left to choose from, but we're interested in an orange one. And there are 5 orange ones, so 5 out of 15 for that. So that reduces to 5 out of 91. And probability that none are cola. Easiest way to think of this one is again 3 fractions. There's 15 total. There were 6 that are cola, and so therefore there's 9 that are not. And then just count down. There's 14 left, 8 of them are not cola, 13 left, 7 are not cola. And we get 12 over 65. And then here's the at least one again. probability of at least one cola is going to be 1 minus the probability that none are cola. And so, nice thing about the way this question's set up, we just calculated the probability that none are cola. So 1 minus 12 over 65, which gives us 53 over 65. Okay, so that's the end of section 3.2.